Hi, welcome to the exida OEMX video. Today we're going to talk about how to use ARCHx to gather up all the design information that you need for a top quality efficient FMEDA. ARCHx and FMEDA-X are both applications in the OEMX suite. What's nice about these two is they play well together. If you use ARCHx to gather up your design information, it automatically provides that information to FMEDA-X when you need it, saving a lot of engineering time as well as documenting your design results. Now, what information am I talking about? Well, when we look at a device, a product, an embedded controller, or a sensor assembly, we've got to know what automatic diagnostics are planned for this device. We need to thoroughly understand the architecture design, and we need to see what design blocks exist and what are the functions of such design blocks, so we can determine device level impact of functional failures. Given a set of automatic diagnostic mitigations, how good is that diagnostic for the specific block failure mode? I mean, diagnostics can be more or less effective depending on the block functionality. We need to know what happens when a failure is detected, what action is taken at the device level, and we want an FMEDA that accounts for the failure rates even after what's called a latent fault test. So we need to define latent fault tests and define latent fault test effectiveness. How good is this latent fault test for each specific failure mode of each specific block? Boy, sounds complicated. I know a lot of you guys probably haven't even done that in your FMEDAs, but you're missing a lot of accuracy. Let's look at the architecture on this power supply subsystem from a controller module. I see 5 function blocks, and we need to know the blocks, how they're connected, okay, and what is the function of each block. I can see if this is the information we've been given. This designer has done a good job documenting the architecture design. Now, what do we do with this in ARCHx? For each block in the architecture, which we call a unit, we will enter that information into ARCHx, using the load unit knowledge feature. In load unit knowledge, we enter the name of the block, pick a block knowledge type, and as soon as we pick a block knowledge type, ARCHx displays failure modes, known failure modes, and proven mitigations. We can select the failure modes that are applicable and the mitigations that are applicable in our design and load that unit knowledge into the device architecture tree. When we get down through all the units, we will have a good complete list of all the automatic diagnostics planned for this device, and they're documented properly. And I'll explain a little more about that later. And it was done fast and effectively using helper checklists. Then, once we have a unit entered, we're going to look at each of the failure modes and classify the impact. By knowing the functionality and knowing the failure mode, we can then classify the impact of that block and that failure mode on the device. In this particular case, loss of a power supply input is the controller goes dead. That's a dangerous fault, so we select that from our pull-down list, and when we're all done, we'll have a list of all the blocks, the units, the unit failure modes, and the impact of each unit failure mode. Great. Now for automatic diagnostic mitigations, we also want to know how good is this deviation. How good is this mitigation for this particular failure mode of this particular block? And we load the mitigation screen. There is a selection defaulted, and the knowledge base suggests the coverage for you. We check that and make sure it's straight. If we have what we want, we check the action taken, which is suggested for you. And if that's appropriate, we now have diagnostic coverage effectiveness and action taken. It can go pretty fast. The action taken list comes from another pull-down list, which is right here, and you can pick one of the standard ones or type in your own custom action taken. Wow. We got through that pretty fast, and yeah, that's the point of it all. That's why a smart knowledge base is such a valuable tool. The latent fault test, what is it? Well, sometimes you can't detect all potentially dangerous failures in a product while it's operating. But sometimes you can do additional tests, manual, semi-manual, automatic, when it's not operating, and we call those latent fault or proof tests. Well, in order to put that into your FMEDA, you've got to define the latent fault tests and estimate their effectiveness. So in ARCHx, there is a place in the deviation node editor to enter your latent fault tests and estimate your latent fault test coverage. There's a latent fault test editor where you can explain in detail what you meant by this particular latent fault test, even with some specific test procedures. It goes pretty fast, a whole lot faster than digging through reams of design documentation, and a whole lot faster than an incident that occurred some weeks ago where Exida received a 200-page DFMEA, and we had to try to traipse through that to extract what we wanted. Not good. Kind of a real waste of engineering time, but anyway. When you get all the design information into ARCHx, it's available for FMEDA. For example, when I'm converting component failure, when I'm looking at the impact of component-specific failure modes on a device, the block failure modes are presented automatically. They come right out of ARCHx. And I'll show you what we mean by that with a quick demo. Let me bring in ARCHx, or the OEMX software. Going to go ahead and go full screen. Let's start by loading up a block of unit knowledge. So this is my power supply subsystem block 1. What kind of a block is this? Well, it's a power monitor. No, it's a power protection circuit. We've got there we go, power conditioning. Now, sometimes there's a lot of not different types in the knowledge base, so you can certainly go up and put in a knowledge filter. And now when I go to select much shorter list, things that have to do with power, I pick power conditioning, failure modes, mitigations, they're all there. Now, you got to think. This tool is not an excuse for not thinking. This isn't a check the box kind of thing. You got to look at every failure mode and see what makes sense. Power supply connector. I'm going to cover that. That's going to be covered later, so I'm going to delete that. I know I want overcurrent limiting. I know the design has a connector keying. I know the design has intended to have voltage clamping and low undervoltage monitoring. So I'll load this with the subtree with the requirements. Great. First unit, structure established. Then you look at each deviation, pick the appropriate impact at the device level. Overcurrent drawn, that's liable to stop the safety function. So we're going to make that dangerous. Now there's a lot of other stuff you can enter here. The potential effect, a cause. You might make your best estimate of likelihood and severity. These aren't necessary for the FMEDA, but if you need to generate a spreadsheet version of an FMECA, or what many call a DFMEA, you can enter this additional information, and it's used to automatically export FMECA spreadsheets. But for the now, we're working on FMEDA, and we're just going to keep rolling. There is a place, we don't have any latent fault tests. We may have to come back later to do that, but I want to see what's going on. So I'm going to run down through the rest of these. Reverse polarity. Oh, we have protection against that. But if somehow the connector is reversed, that's going to be dangerous. Don't worry. I'm going to get that later. Over voltage. We have a transient suppressor, but that's going to be dangerous also. And loss of the power supply input is clearly going to be dangerous. I'm not going to bother with cause, the effect, likelihood, or severity, because for the moment the FMEDA is going to answer the priority questions. All right, good. We have one automatic diagnostic. Let's look at the input voltage monitoring. We assumed it's a simple comparator type circuit. The high diagnostic coverage is completely justified. We can even put in a note if we want to detail it out. Oh, I think we do have to spell things. It's best if you spell things correctly. Good. Good. We could define an integration test if we want right now, but we're working on our FMEDA. That's it. We've gathered all the design information needed for an FMEDA. Now, there's one thing I want to show you. I went to ARCHx, and I see the mitigations we selected are listed here. Well, we don't want any of these to be missed. We want them implemented as we basically assumed. And so we want to move these over into requirements, and we can use this tool to put them into ARCHx and write reports that we can use to copy and paste into any other requirements tool if you're not using ARCHx. But for the moment, it's important we don't lose the list of mitigations we have chosen. Now, let me pretend I have a schematic and a bill of material, and we're going to start entering some parts for the power conditioning module, or a block, I should say. And we'll go to the Add Component menu, and let's look at the terminal strip. All right, and that's a I need to pick the component. What kind of component is this? Well, it's part of the electrical database for sure. And oh, wow. Yeah, that's very impressive. There's a lot of components in this database. Holy smokes. Well, I can do a shortcut by typing in a little filter. For connectors, let's just see what happened to my list. Oh, nice short list. A terminal strip is a type of connector. I'm going to assign the CRD, which now selects the part. I've got a failure rate, I've got the failure modes and the failure rate per failure modes. But I've got to stop and look here to these design strength options. I know that I have 3 screw terminals, shield, minus, and plus. We're not using gold contacts here. This is probably tin. Yeah, there it is, tin contacts. Well, I see 3 fits up there. Whoa, it just went from 3 to 9, and of course, that's a design strength option, which takes into account the all the environmental stress factors that we've listed. Okay, that's good. Everything else lines up. Now, I have to map this component failure mode short circuit on the connector. Let's assume worst case, plus to minus. Well, we're certainly going to lose power, and there's probably going to be trouble upstream, but we could just right now call that dangerous if we know it, but we've already done the work. So look at this. The failure modes of this block are presented for us. And that makes it much easier because I know if that screw terminal shorts plus to minus, I'm going to lose my power supply. If it goes open, same thing. I have just mapped the failure modes of the component into the failure modes of the block, and everything else will be done automatically for us. Great. We keep going with all the other units and all the other components, and we're going to get a nice clean. I'm not going to save this one. We're going to get a nice clean FMEDA. Thank you for your time. If you have any questions, don't hesitate to send an email to oemx@exida.com. Right now, while this video is fresh in your mind, you should go play with your demo version. If you don't have a demo version, use the same email address to check for one. Thank you for your time. I hope all is well with you. Take care. Bye-bye.